solve is not the super saturation as was in the case of the cloud chamber, but it is superheating. Superheating is a phenomena when the temperature of say a liquid is greater than the boiling point of that particular liquid. Okay, so if you heat the liquid in equilibrium, पानी आपने रखा सपोज गैस के ऊपर, आप उसको हीट कर रहे हैं, तो पानी क्या होगा, 100 के आसपास आने पे वो बॉयल होना शुरू हो जाएगा और अल्टीमेटली इट विल वेपराइज ऑल ऑफ दैट. बट इफ सपोज द लिक्विड इज जस्ट बिलो द बॉइलिंग पॉइंट, आपने क्या किया, उसको 96 97 डिग्रीज पे रखा कांस्टेंट, बहुत स्लो हीटिंग की और कांस्टेंट 96 पे फिक्स कर दिया, so it is very close to boiling point but it is less than, so it will not thermodynamically it will not boil, right. अब आपने क्या किया कि जो सराउंडिंग है, सिस्टम के सराउंडिंग जो प्रेशर है उसको आपने डिक्रीज कर दिया, पिस्टन मूव करके सडनली डिक्रीज कर दिया. अब क्या है कि द टेम्परेचर तो सेम है 98 से डिग्री सेंटीग्रेड, लेकिन जो बॉइलिंग पॉइंट है लिक्विड का, क्योंकि प्रेशर कम है सराउंडिंग में, तो बॉइलिंग पॉइंट उसका से 96 डिग्री सेंटीग्रेड हो गया. अब जब 96 डिग्री सेंटीग्रेड पानी का टेम्परेचर है और पानी एक्चुअली 98 डिग्री पे है, तो ये जो रिवर्स कंडीशन है कि ये जो मैटर है वो लिक्विड स्टेट में है पानी, और उसका जो एक्चुअल टेम्परेचर इट इज हायर देन द बॉइलिंग पॉइंट. So this strange condition is known as superheating. Okay, so अब ये superheating है liquid, अब it will not spontaneously vaporize. Okay, spontaneously vaporize.
Excuse me, sir.
Yes.
Sir, am I audible?
Yes. Please, Mahika. Go on.
Sir, there is a doubt.
हाँ, please बताइए.
सर, जो ये कंडीशन क्रिएट किया है हमने सुपर हीटेड स्टेट,
हाँ,
ये अचीव करने में तो ऐसे समझ आ रही है कि इस पहले उसका खुद का बॉइलिंग पॉइंट 78 था, हमने बॉइलिंग पॉइंट कम करके उसको
हाँ.
ऐसे स्टेज पे लेकर आए जहाँ पर टेम्परेचर बॉइलिंग पॉइंट से भी ज्यादा है बट स्टिल वो लिक्विड फॉर्म में ही है,
ठीक है, ठीक.
एग्जिस्ट कर रही है.
हाँ,
बट सर इसको ये तो तब हुआ ना जब क्विक प्रोसेस हुई, इसके बाद इसको मेंटेन, क्योंकि इसके बाद तो आने वाले थोड़े से टाइम में तो वो बॉईल होना शुरू हो जाएगा जब उसको रियलाइज होगा कि हाँ अब मेरा
हाँ.
टेम्परेचर कम है, तो वो उसको मेंटेन कैसे कर पाएंगे?
सुनिए, यहीं पर ये आई मीन दिस इज वेयर द thermodynamics come in. Unless there is, I mean, you can do this heating, I mean this kind of superheating in keeping the water in say microwave, heat it quickly, and bring if we bring that up, I mean out of the microwave, the heating is very quick but it will not boil. And if you know drop a small amount of salt or small amount of sugar or any other powder in that, the interaction of the salt, sugar or dust particle with the liquid provide the interface for the formation of the gas. So gaseous phase will nucleate only when the interface is available, which is different from already what is there. जो पहले से है वो सारा थर्मोडायनामिक इक्विलिब्रियम में है, और उस इक्विलिब्रियम में द लिक्विड इज इन लिक्विड स्टेट, एंड व्हेन यू चेंज द कंडीशन, system the boiling point is comes down, but there has to be some trigger to form these bubbles. And in the bubble chamber, this trigger is actually comes in the form of the particles that are either colliding with one another and fragments of those particles, or the simple passage of the ions from the chamber. Okay, तो ये सुपर हीटिंग की जो कंडीशन है इसमें वी नीड ए ट्रिगर इन ऑर्डर टू form the phase which is actually stable at that temperature. So the phase stable at this temperature is these bubbles, but there we need some trigger in order to stabilize that phase. So this trigger comes in the form of these ions or the fragment of those ions as a result of the collision between two high energy particles moving in opposite directions. So this is how, I mean, these are small, what we see the trails here, all these small bubbles, these are the bubbles that are formed as a result of the passage. Because this is a straight line, there is nothing, no fragments thereof that are coming. We'll see in the next few slides what happens, because let's say there is a curvature. Okay, so with a curvature we know the momentum p is proportional to the radius. So we cannot actually look at the momentum directly, but from the photograph we can see what is the curvature of the bubbles, and from these bubbles we can correlate the curvature to the momentum of the particle, and we know the velocity from the videography, etc. We can know the mass of the particle. Okay, so that way this is bubble chamber actually works. So Mahika, I hope it is clear.
Yes, sir.
So I will try to send the link for this activity, which is done the microwave superheating and the bubbling thereof after addition of sugar and olive oil. I'll try to find it out. Generally, it should be available. But this is actually interesting. This 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 formation of bubbles. So unlike the cloud chamber, this bubble chamber could not be triggered. That is, bubble chamber had to be already a superheated state when the particles were entering. So before the particles, high energy particles entering, they need to be superheated, and these particles need to be these superheated liquid need to be triggered. It is not automatically triggered to boil thereof. So it was therefore used for these detection. These are the actual tracks of these particles. You can see at this particular location. What we can see, there are a lot of tracks. Suppose this one, initially this one, this. Uh, all of these particles have same kind of curvature. So it's like this here, here. All of these are uh, going with the same kind of curvature. One of say one is uh, kind of disintegrating and generating further particles here, and the other one is generating right here, and then there is something happening here, and so on. These cross represents the magnetic field that goes perpendicular to the plane of the paper. So as a result, because p from mv square by r is equal to b e v, so mv square. So we can see that this mv is equal to b e r. So magnetic field and the charge is constant. So this momentum is proportional to the radius. So this radius of the path is important, and that tell us what is the momentum of the charged particle. And if we could identify the velocity by taking the V's at all, and from the energy of the particle also we know the velocity. So it can be confirmed by high scan rate these videos. So the mass of the particle can be identified. So we can basically know what kind of charged particle are being generated. So there are various, like we saw in case of these art. So the particles with small radius, that means they have a small mass. So depending upon their spiral, the mass can be correlated to are observed here. This is the actual photograph, basically given in say 1956, where this in the propane chamber, the discover the sigma zero, and all these particles were detected. So let me, yeah, this is how the momentum is proportional to this. And now, if you look at again this, uh, suppose at this particular point, these are there's a disintegration, and this particle goes onto the say one side. This is supposed to be the alpha particle, because it goes to one direction, and then it simply terminates. And all these are the small uh, these curves are because of the knocking off electrons, and the the spiraling of the electron happens because of the generation of these kind of radiations, and ultimately the charged particles lose all. This is say in the reverse direction. Here the particle was kind of downward, the upward, and what it means, because there is a reverse directions to which these two uh, the lines are emanating, or so it implies there are oppositely charged kind of particles that are generated here. So as compared to this, the bubble chamber, this is the 80-inch bubble chamber pictured at the Brookhaven National Laboratory in 1963, having the uh, 3 or 30 millisecond has this cycle. So this is the bubble chamber, and this is the actual photograph uh, taken by the bubble chamber, where all these tracks are uh, analyzed and deciphered to be associated with all the respective particles that are written alongside with the track. And this was happened in 1964, following the images taken at the Brookhaven, and the, the particle Vega I was discovered in 1964, and for which the Nobel Prize was uh, so in 1964, the which is known as the omega baryon was discovered, and which was made of these three strange quarks, and this the image was taken by the say bubble chamber. So it's a what we know is the kind of a three-dimensional chamber where the gas is filled. There are few other. Uh, this is the picture of the bubble chamber. So this is suppose freon side is the freon heavy liquid freon chamber constructed in Paris in 1970s, and this is how the construction looks like. There is a camera attached to the chamber, and this is the piston that moves up and downwards, and uh, there are the superconducting magnets used to apply the high magnetic field uh, in the chamber, and these are so this is the actual chamber, the photograph taken in the bubble chamber, and the tracks that are assigned to various particles. So all the conservation parity principles. This is another bubble chamber at CERN, having largest superconducting magnets. It was working till 1980. So this we can take. So yeah, these are some of the other. We can summarize with the observation that the bubble chamber, which is made up of all the full the tank. Uh, this chamber is made up of a liquid just below the boiling point, and on which the high magnetic field is applied, and with the movement of this piston, the liquid in the chamber is super heated, and as the ion pass through the chamber, there are these bubble formation, and the ions or the particles that are generated, they act as the interface for the nucleation of the stable phase in the bubble chamber. So applying various principles, the of the say specific charge, and the conservation of mass, energy, etc. Uh, so the different type of particles are actually deciphered using the images taken from the bubble chamber. So magnetic field is used to curve the trajectory and so on. So this is about the bubble chamber. Uh, Basically, what is important here is the working. You can write all this. You can make the diagram. This is the schematic diagram. If more uh, more more detailed image need to be drawn, you can draw from the bubble chamber given in this image. And so it works on the principle of formation and the trails generated thereof. From the trails, the various curvatures in the trails, particles are detected. Various particles are detected. Uh, so this is about the bubble chamber, and I should be sending you super heating. So let me look at for the same in a bit of time. By the time you please, if you have any doubts, please let me know.
एक्सक्यूज मी सर, आपकी आवाज नहीं आ रही सर।
हाँ हाँ, अभी हरीश अगर कोई डाउट है तो आप मुझे पूछिए, और I'm looking for the superheating of water in the microwave, so that we can see if actually I could find out.
Excuse me, sir. Hello. Excuse me, sir.
Yes, yes, yes.
Uh, Sir, if we can say it is a kind of observation to quantum particles. तो सर हम न्यूटन्स लॉज कैसे अप्लाई कर सकते हैं? तो उसमें तो फिर पुट उसमें मोमेंटम में तो फिर एरर आ जाएगा। मोमेंटम और फिर उसकी उसमें रेट में और फिर मास में एरर आ जाएगा, तो फिर हम वो एरर को ओवरकम कैसे करेंगे?
Yes, yes. देखिए, if the charged particles that are colliding, they are traveling at relativistic say velocities, definitely the momentum proportional to say the radius doesn't hold, and that's how what we see is the spiraling, right? The radius is not constant. So say from that point of interaction, because you see there is liquid and the particle is continuously losing energy, therefore the velocity is also say decreasing. Okay, so this is I mean how this is an approximation. It is proportional, but the proportionality constant take care of the other things that are variable. uh, but these this can be used as a starting point to analyze the images. For analysis, there is a whole detailed physics that is required, but we are not concerned with the analysis of the images per se, but how the detection happens, how the formation of the bubbles happen, and once the bubbles are there, the trail is there, the photograph is taken or the video is taken and then further analyzed. Okay, so let me show you if I can. We can have the microwave water exploring water. uh, so superheating water, yeah. Let me, so if you can see this, see, I am also seeing this first time in this video, but let us see what he says. Am I this the sound from the video is audible?
No, sir. No, sir.
I think there is something need to be redone. I think it should be visible now.
On purge. And today we're gonna need a lot more safety, like face
Is it audible now?
Yes, sir.
and gloves. We don't want to burn ourselves. Yesterday I made water explode and I asked you how does it work or how to do it. Quite a few people know this thing, but a lot of don't. So right now I'm gonna show you how to do it. All we're gonna need is distilled water and microwave and any kind of object to throw in the water. So let's get to it. First we're gonna put distilled water into the glass. Then we're gonna put the glass in the microwave. And this kind of glass will take about 4 minutes first to heat it up and we're gonna add some sugar in our tea. And guess what? Your tea would explode and burn you. Check it out, we got glass of water and we're gonna drop a coin and see what happens. Water exploded. Alright, that's it. Let me know what you think, comments below. Don't forget, give me a like if you like that video. And you know, you don't want to microwave distilled water.
Okay, let us look at another this thing. Superheated water can explode outside microwave. Okay, so this is very quick small video. So what we see, this is the water that is just brought out of the microwave, and boiling. If we see it, it's not boiling. Prior to it is being added into that, the moment it is added, now depending on how much super. That is the external this thing. There is another.
This time on A Moment of Science, exploding water.
A moment of science.
You're not gonna make coffee with that, are you?
There are stories of people who have put a cup of water into the microwave to bring it to a boil before adding tea or coffee, only to take it out of the oven and have the water erupt in their faces, causing serious injury. Fact or fiction?
That is malarkey. I needed extra boiling for my aged Sentinel yeast triple milled blend.
No, it's true. It can blow up and burn you. And I don't trust that coffee either. You got it from Craigslist.
Well, actually, it's totally possible. To understand how this happens, we need to quickly review what boiling is. When water is heated to the boiling point, the liquid water changes to gas, thereby expanding its volume greatly. Boiling is the expanding of the water molecules into the gas bubbles. However, for these bubbles to form, there must be something like bits of dust in your kitchen, a tea bag, or rough sides on the container for them to form on.
I'll have you know, that mug is a Third Nubian Empire replica, specifically manufactured for coffee you can't appreciate.
I got you that mug at a yard sale.
If the container you use to heat the water is new or highly glazed, it might have very smooth sides and no rough places on which bubbles can form. If it's very clean, there might not even be bits of dust for the bubble to form on. Without these, there'll be no bubbles forming and rising to the top to break the surface and allow steam to escape. And the water can continue to heat up past its boiling point to what's called a superheated state. The surface of the water literally holds the heat in like a lid. So when the water surface is finally disturbed by moving the cup or putting a tea bag in, the superheated water instantly and explosively comes to a boil, throwing steam and very hot water all over. Yikes. So just to be safe, if you plan to heat water in a microwave, put something non-metallic in the cup, like a wooden stirring stick or a tea bag. Or, be even safer, skip the microwave and heat the water on a stove in a tea kettle. I'm Mandy Strife, and this has been A Moment of Science.
Okay, they have not actually demonstrated if just the nuclear explosion was the exaggeration.
Science.
For more interesting science facts, visit our website at A Moment of Science.
Okay, so you can look for the similar material and get yourself a little more than this. So this is what we had for today. We will continue with the next detector in the next class, which is the nuclear emulsion. I would like you to read about it before the class so that there could be a little more happening discussion. Okay, so with this I am ending the class. Please take care. Okay.